What is a distributed rate limiter? A distributed rate limiter is a system that enforces rate limits across multiple distributed nodes or servers in a system. It ensures that the rate of requests from users, APIs, or services does not exceed predefined limits, even when the system is running on multiple servers or in a distributed architecture. How does it work? A distributed rate limiter uses a combination of distributed storage, algorithms, and synchronization mechanisms to enforce limits across nodes. Here's a breakdown of its functioning. 1. Core components. 1. Request identification. Each request is identified based on a key, such as user ID, API key, IP address. 2. Rate limit definition. Limits are defined based on number of requests allowed per time window, e.g. 100 requests per second, sliding window, fixed window, or token bucket models. 3. Centralized or distributed storage. A consistent distributed data store, e.g. Redis, DynamoDB, or etcd, is used to share and synchronize counters or tokens across nodes. 2. Common rate limiting algorithms. 1. Token bucket. A bucket is filled with tokens at a fixed rate. Each request consumes a token, and if the bucket is empty, the request is rejected. 2. Leaky bucket. Requests are processed at a constant rate. Excess requests are queued, and if the queue is full, requests are dropped. 3. Fixed window. The number of requests is counted within a fixed time window, e.g. 1 second. All nodes synchronize their counters to ensure global rate limits. 4. Sliding window. Instead of fixed windows, this uses overlapping time windows for smoother enforcement. It ensures fairness by counting requests over the last rolling time period. Workflow in a distributed system. 1. Request routing. Incoming requests are routed to different nodes, servers in the system. 2. Shared counter token synchronization. Each node checks the request against a global counter or token pool stored in a distributed database or cache. Example, Redis or a distributed NoSQL database like DynamoDB is commonly used for shared state management. 3. Rate limit enforcement. If the counter tokens exceed the defined rate limit, the request is denied, e.g. HTTP 429, too many requests. Otherwise, the counter is incremented, or tokens are consumed and the request is processed. 4. Synchronization across nodes. Nodes communicate with the distributed storage layer to maintain a consistent view of the counter's tokens across the system. For example implementation, using Redis for token bucket algorithm. 1. Storage in Redis. Redis stores a token count for each key, e.g. user 1234 tokens. 2. Request handling. When a request arrives, the node checks Redis to see if tokens are available. If tokens are available, one token is consumed and the request is allowed. If no tokens are available, the request is rejected. 3. Token refill. A background process or Redis Lua script periodically refills tokens at the defined rate. 4. Synchronization. Since Redis is centralized or replicated, all nodes share the same token pool. Challenges in distributed rate limiting. 1. Latency. Accessing centralized storage like Redis can add latency to request handling. 2. Consistency. Distributed systems may face issues with eventual consistency, leading to temporary overshooting of limits. 3. Scalability. High traffic systems need highly scalable and low latency storage for counters or tokens. 4. Fault tolerance. The system must handle node or storage failures without losing the ability to enforce limits. Optimization techniques. 1. Local caching. Nodes maintain local counters to reduce frequent access to the distributed storage. Local counters periodically synchronize with the central store. 2. Partitioned keys. Keys are partitioned across nodes to reduce contention and load on the central store. 3. Multi-layer rate limiting. Combine global, distributed limits with local, per node, limits for faster enforcement. Use cases. 1. API rate limiting. Prevent abuse or overuse of APIs by limiting requests per user or service. 2. Login authentication throttling. Limit login attempts to prevent brute force attacks. 3. Content delivery networks, CDNs. Manage traffic from multiple clients to prevent overload. 4. Distributed microservices. Throttle inter-service communication to maintain stability. Conclusion. Distributed rate limiting ensures consistent and fair enforcement of limits across a distributed system. By leveraging algorithms like Token Bucket and storage systems like Redis, it provides a scalable and reliable way to control traffic, protect resources, and enhance system stability.